Let's take a look at the law of conservation of energy. So with the energy skater going back and forth, we saw that at the top, his energy is all potential energy. As he's going down, by the time he's halfway down, half of his energy is potential and half of it has been converted to kinetic. By the time that he gets to the bottom, all of his potential energy has been converted into kinetic energy. So we can see, however, that the total amount of potential energy that he started with at the top, I shouldn't say the total amount, but the potential energy that he started with at the top equals the kinetic energy that he ends up with at the bottom. So as far as patterns go, that's a big one. The potential energy at the top equals the kinetic energy at the bottom. So go ahead and pause and take a moment to record this observation. Okay, welcome back. So we can describe this using mathematical symbols as well. Potential energy, PE, equals kinetic energy, KE. Okay, and potential energy at the top, we can write top in a little subscript and KE a little subscript. And let me just bring this KE a little closer here. Oops. Not that one. Let me try that again. Let's bring the KE a little closer. There. Okay. All right. So now this leads us to the law of conservation of energy. Actually, what leads us to this law is the fact or the observation that the total energy here doesn't change. The total energy here is the same no matter what forms of energy are present in the system, because those forms of energy are just converting to and from each other. So the fact that that total energy remains constant means that the total energy is conserved. So the law of conservation of energy says that the total energy of a system is constant. That's what that word conserved means. As long as no work is done on or by the system. What do we mean by work? We defined energy as the ability to do work. And so when this skater is going back and forth, it has kinetic energy. Now, if you were to add like whatever it might be, let's just say like a snowman at the bottom of the ramp, the skater would hit the snowman and they would be doing work on probably breaking the snowman. And that's going to decrease their speed. So they will be losing energy as they use their energy to change the snowman. That would be an example of work done by the system. So doing work by the system causes the total energy to decrease. Doing work on a system causes the total energy to increase. An example of doing work on the system would be if, say, they had a friend who was giving them a push every time they got to the top of the ramp. That means they would go faster down the ramp after the push, and then they would go higher up the other side of the ramp than they did the last time. So in that way, the work that their friend is doing in pushing them would increase their energy. So that would be an example of work done on the system. Now this law of conservation of energy can be written as an equation. And so the total energy before equals the total energy after. Because what we're saying is that the total energy is not changing. And in our particular case, what is the type of energy that we're looking at? We have potential energy and we have kinetic energy. we're going to leave thermal energy out of the picture for now, for simplicity. So there'll be no friction. So potential energy plus kinetic energy before equals potential energy plus kinetic energy after. And what do we mean by before or after? It just means before or after any particular thing happens. So it could be before the skater drops down the ramp, and then after would be when it gets to the bottom of the ramp. So the units for this is the same units as energy in any of its forms, which is the joule. And the symbol for joule is capital J. But it doesn't have to be joules. That's just a metric, or SI unit, which stands for International System of Units. But you can also have the calorie, which is the English system or English unit of energy. But we'll pretty much always work with joules. Let's take a look at example 1. A 50-kilogram skater starts from a height of 5 meters. How much kinetic energy will he have at the bottom of the ramp? So let's just underline some information that might be relevant here. So we have 50-kilogram skater, and we can recognize that that's his mass, and the height of 5 meters. Okay, so we're being asked to find how much kinetic energy will he have at the bottom. And we do know that there's an equation for kinetic energy which says kinetic energy equals 1/2 times mass times velocity squared. We do know his mass. We don't know his speed. And because of this, we cannot use this approach. It's not going to work because we don't know V. So is there another way that we can do this? And yes, there is. We can use the law of conservation of energy, because the kinetic energy that it'll have at the bottom, we know is going to equal the potential energy that he has at the top. And we know that from our observation before. So because of that, what we're really doing is just calculating his potential energy at the top to then know what his kinetic energy will be at the bottom. So now we can do potential energy is mass times gravitational acceleration times height, and that equals 50 kilograms, which we took from up here, times g is 9.8 meters per second square, it's gravitational acceleration, times height, which is 5 meters, which we got from up here. And if we do the math on this, 50 times 5 is 2,500 times 9.8. Oh, let's see here. I'm going to pause. No, I can't pause. I'm going to open up my calculator app. Oh, here we go. And that was 50 times 2,500 times 9.8 equals 1,225,000. And the units for that would be joules. Okay, the next question is how much speed will he have at the bottom of the ramp? And we should think about what information we have. So now we have V equals question mark. We do know, we know that his kinetic energy is 1,225,000 joules. And we also do know that this equation for kinetic energy, sorry, I forgot to put KE. We also know that the equation for kinetic energy is 1/2 times the mass times the velocity squared. So, we could do we have enough information to solve this? So we know the kinetic energy, we know the mass, and that allows us to solve for velocity. And we're going to use algebra to do that. So let's work through the algebra steps that we would need in order to solve for velocity. Okay, I'm going to first have us substitute in the values that we know. I feel like that might be a more usual way for you to think of this. So kinetic energy is 1,225,000. We'll leave units out of this just for simplicity. Equals 1/2 times the mass, which is 50, times v squared. And so now we need to simplify this. So how about 1/2 times 50 is 25. And remember, for 1/2, you can always use that as a decimal. 1/2 equals 0.5. Okay, and then on the other side we have the same as before. And then we can do an algebra step. I'll show that algebra step in a different color just so you can see that it's algebra and it's not just a simplification. So we divide left and right side, or sorry, we divide top and bottom by 25 on the right side. And what we end up with is v squared equals, I'm going to go back to my calculator app, divide this by 25, we get 49,000. And that's v squared. We have one more step to do here, which is take the square root of both sides, because the square root of v squared is v. And as long as we're doing the same thing to both sides in algebra, that's a-okay. Do unto on one side as you do unto the other. So now we go back to our calculator app, square root of 49,000. I'm going to do the square root of that, which is right here. And I get 221, which sounds too big. What's going on here, Mr. Geller? 221 meters per second. I feel like I made a big mistake somewhere. And, yeah, okay. I think this number is totally wrong. 50 times 9.8 times 5 is not that big of a joules. I should have caught that. It seemed too big. So let's find out what that really is. I would have been better off doing it in my head. So 50, no, it was, yeah, 50 for the mass times 9.8 for gravitational acceleration times 5 for the height is 2450. So let's see here. Yeah, way off. And I knew that because 221 meters per second is just way too fast. So what was that number again? 2450. Okay. So 2450, 2,450 that is. And divide that by 25. 98. And take the square root of 98. 9.9. That sounds like a more reasonable speed. 9.9 meters per second. Okay, so we have succeeded in calculating a prediction of what his speed would be at the bottom. Now keep in mind, this is his maximum possible speed at the bottom, given how much potential energy he started with. If there's any friction, his speed at the bottom is going to be less, because some of that potential energy will get converted into thermal energy, leaving less available as kinetic energy. All right, so the next part here is, was there a shorter way to determine his speed at the bottom? And the answer is yes. And we'll make that part 2. So I'm going to stop this video and start part 2.